Hello, and welcome to this MCMA webinar, What's New in Motion Control Applications. My name is Joanna, and I will be serving as your moderator today. Attendees that have joined this webinar have joined in listen-only mode, which means that you are muted. If you do have a question during the webinar, please submit them in your questions panel, and we will answer all questions at the end of this webinar. This webinar will be recorded and a link will be sent to you within the next 24 hours. And now I'd like to thank our sponsors. Kollmorgen. Since its founding in 1916, Kollmorgen's innovative solutions have brought big ideas to life, kept the world safer, and improved people's lives. Today, its world-class knowledge of motion systems and components, industry-leading quality, and deep expertise in linking and integrating standard and custom products continually delivers breakthrough solutions that are unmatched in performance, reliability, and ease of use. Products like Kollmorgen's AKMH hygienic servo motors, PMX series stepper motors, AKD PCMM standalone motion controller gives machine builders around the world an irrefutable marketplace advantage and provides their customers with ultimate peace of mind. Nexcom. Founded in 1992, Nexcom's mission is to be a quality partner in engineering, manufacturing, and services to enable its customers to successfully deploy key projects in a diverse range of industries. Nexcom provides a wide range of computing solutions for increasing demands of industrial environments. Those solutions include embedded computing, powerful fanless computers, industrial rack mount computers, industrial wireless solutions, machine automation, panel PCs, and PC-based factory automation. Nexen Group is a leading manufacturer of precision motion control components, power transmission, and web tension control products for a wide array of industrial applications. Products include high-precision linear and rotary systems, linear locking components, pneumatic brakes and clutches, torque limiters, and electronic tension controls. Nexen customers span every industry including aerospace, robotics, machine tool, automotive, factory automation, packaging, and material handling. And now I'd like to introduce our presenter of today's webinar, Kristen Lewatsky. Kristen is a contributing editor for Motion Control Online and has written about motion control and automation for more than 7 years. As a technical writer, she covers a variety of subjects, ranging from memory and microelectronics to nanotechnology to laser and photonics. Kristen previously worked as an engineer on NASA's Chandra X-ray telescope before switching to writing about technology. Kristen holds a Bachelor of Science degree in physics and a master's in optics and photonics from the University of Central Florida. And with that, I'd like to hand it over to Kristen to go ahead and get us started.
All right, so let's see. We are going to talk about what's new in applications today. Normally, when I do these kinds of stories, I get on the phone with a bunch of people, and what I mostly expected to hear about was a lot of different new applications, things that were going on different, and interestingly, what people talked about first and foremost was nuances to the technology and how that's feeding into the new application areas and so on. And it kind of makes sense if you take a look at what's going on in the world of the end users. Certainly the Great Recession changed things for everyone in terms of the economy as far as financial aspects and so on. But there's also kind of the way people are using technology these days and what they expect. I mean, in your personal life, you expect things to be very custom. You expect things to turn over quickly. You know, the latest and greatest new technology is constantly served up and done at a very low price. And part of what that's been doing is also schooling everybody in the industrial end to really start expecting that kind of value proposition in their working lives. So there's a lot more pressure from the standpoint of consumers of motion control technology to have that kind of customization and ease of use and fast turnover and so on, so that they can address their customer base and give them what they're looking for. Unfortunately, with the market forces, they're also facing some definite market realities. You've got very tight budgets. People have moved to lean manufacturing modes so that they don't sit on a ton of inventory, and what that means is you need much, much more flexible technology so that you can quickly turn over from producing one thing to the next, as opposed to having a whole lot of stock. At the same time, companies are increasingly trying to do that with much less deep staffing. So your OEMs don't have quite the levels of technical expertise that they once did, ditto for the end users. And that can, it works for them in that they're trying to really put their engineering dollars and man hours or person hours against their core value proposition as opposed to motion, which is kind of an enabling technology. So that's one factor. The other factor is depending on the industry. If it's, some of your heavy industries, steel, wood processing, whatever, they may never have had people on board that were doing hardcore motion control. They might have been really happy to stick with some of the more basic stuff because they didn't have the staffing expertise. And then the other factor that's going on with all of these organizations is they're trying to make sure that their dollars are going to maximize productivity and so on. Looking at factors like OEE, and since I had a slide drift, we're going to have to run back up. Just tag the base of OEE for anybody out there who's not aware. That's the metric, one common metric used for tracking how well your equipment is doing at putting out stuff for you to make and sell and make money off of, basically. And it's a combination of availability, what keeps your stuff up and running, performance, how effectively does it push out material, what is your throughput like, and quality, of course, because it's not going to matter whether you get a ton of product if the product's no good and it can't be sold. So let's sit down where we want to go. So motion control, in general, as I said, with these technology developments, vendors have really been looking to come up with solutions that are aimed at delivering better performance, more flexibility, particularly ease of use, and also supplying engineering services or guidance. I mean, companies can certainly go to integrators for things like that, but a lot more motion vendors that I talk to are working very tightly with their customers. And this goes back to that earlier slide where you're talking about lighter engineering staff. So they need stuff that is easier to get out of the box. If you want to move motion technology into a non-traditional area, it's in your best interest to make it easy to use and to give them the tools that they need to apply it to their technology. Some of those that came up in the conversations I was having, auto-tuning drives. Now that's not exactly a wildly new technology, but there's a big difference between when the technology is released and when it sees broad adoption. Also, auto-tuning drives initially quite live up to the billing, so there's been kind of a an upgrading over time. But there are also other aspects to motion systems that give better performance with things like direct drive motors that give you less compliance, and some other technologies we'll be looking at. Safety, again, safety's been around, but some of the options with the new protocols can really deliver some strong value propositions. We'll talk about that. Network devices, and also software tools. Auto-tuning drive, the old way. You get your motor and your drive out of the factory, yay, they're designed to work together, and then you hook up the load, and you got to deal with inertia. And the way it used to have to go is you'd have to exercise the axis and do basically parametric PREDICTIVE, and that was something that could go on and on. It could be straightforward. I've talked to engineers who've said that they literally would spend days on some axes, and that gets even harder when you've got an axis that's going to be loaded in one direction of a motion and unloaded back. So then we get into the ease of use, which is the auto-tuning drives, and there are kind of a couple of flavors of that. You know, you can get the ones that you get straight auto-tuning that comes from the factory. There's a canned sequence that the drive runs through, and that tunes it up. You can also put somebody to work with a screwdriver and get much, much tighter performance. But part of what we're really interested in talking about here right now is some of the more reactive and proactive auto-tuning drives that respond to what's going on in the system, so that they're actually reacting to the real load and following what the encoder is telling them about. Whether they've got error, they're adjusting parameters to drive that error to zero, and that's something that can persist as the drive is operating going forward. And then there's also the variation of being able to respond to a motion sequence, find out what is causing vibration, apply filters to avoid exciting those vibrations, and really dramatically decrease settling time. And that's going to be a key in what we're going to be talking about with the next few applications upcoming. So auto-tuning, you get the drive detecting resonance, and it can run through, change the parameters. You get compensation. It can also, like maintenance, that's something that's going to be important later on when we're talking about predictive and preventative maintenance. But again, the key here is that it's responding. And you can see the kind of effect that you can get where you go from something that would slosh to something that would be very smooth. So when you're looking at applications like electronic pick and place, for example, that's got to be fast point-to-point motion. The faster you do it, the more stuff you can make, the more money you make. So yay, that's all good. But if you get to the point that you're trying to reach and you get a lot of overshoot, you're going to have settling time. That's going to slow everything down, or you're going to impact the quality of your product. And in both cases, that's where the auto-tuning drives can really come in and significantly affect the throughput and the performance there, and do it in a way that's easy. And that's also important earlier about the need to be able to switch from part to part and recipe to recipe. You can do, in theory, this pick and place. You can do that with somebody out there with a screwdriver doing the manual tuning, but every time you change your recipe, you're going to be sending them right back out. If you've got an auto-tuning drive that's got reactive, adaptive tuning capabilities, you don't have to run through that whole process of sending somebody out. The drive's going to do it automatically. And in particular, the drive's going to be able to respond to that loaded versus unloaded scenario that I was talking about earlier. And if you take a look, that can really make a big difference. Here's a pick and place example. And if you start with 50 millisecond settling time, and you take a look up top, you've got the motion lines, or the speed on each direction, and that's 0.7 seconds, and your settling time is 0.1 in both cases, and that runs you up to what, 2250 parts per hour. Now go down below, and if you've got ultra high feedback, that's what can get you to the very, very tight settling times. and I believe this is 1.7 gigahertz feedback on this one. So you get 4 millisecond settling time because you got all of that feedback, and now your settling time goes to, 8 milliseconds. That takes you up to 2542 parts per hour. That takes you to an additional profit of 29.24 per hour. Which doesn't sound like a lot until you start adding it up. You take it to 2 shifts a day, 6 days a week, and that's more than 140 grand annually, and that would be on one axis. So if you start multiplying that, or one part anyway, if you start multiplying that across your facility, you could be looking at very big savings. And again, with these adaptive drives, that's coming through, and it's also coming through easily. 3D printing is another one that came up. I mean, that's, sort of the hype machine is fully behind 3D printing right now. Now, there are a lot of different methods, and there's a stereolithography, and they're doing it with printers and so on. But the key thing in motion that we care about is 2 really common methods, fused deposition modeling and fused filament modeling. And what they do is start with coils. They can also do pellets, a variety of materials, but they're basically thermoplastic. They get fed in to an extrusion head, typically by servo or stepper motors. They get melted, and then the head rasters across the deposition area, and it builds up the part layer by layer. And that's something that can last for hours or even days. They did a case study with Stratasys, 5, 6 years ago now, and they had, at that point in time, a unit that was probably 5 feet by 5 feet, the enclosure, and they told me they had parts that would run for 7 days, putting things together. So, and one of the things that's also interesting here is people are talking about not just doing prototypes with this, but actually broadening it out to manufacturing. But you've got to be able to do it right in this case, and that means you've got to have extremely smooth motion when you're laying down the thread so that you're making the part right, and as it's designed. But the faster you can do point-to-point motion to get to the new position, the faster you can make the part, and you can drive down those run times. And that means minimizing settling, and that goes back to the adaptive drive, adaptive tuning that we've been talking with on the drive. So there's getting to be increasing interest. Now, for a long time, the way to go was stepper motors. They're cheap, they're easy to integrate, they chug along, but you get the longer settling times. You can run them closed loop, but people typically don't. But now there's an increasing trend toward doing servo motors because you got the adaptive drives. If you put on 24-bit encoder, you can have a lot of feedback that's going to help you with those uber short settling times, give you smoother motion. You're going to get faster builds, you're going to get better performance. They're going to be robust enough that give you a long lifetime. So it's all good. Now, talking about the whole issue of usability and make it easy, wood processing is one. Now, actually adding it up, I think I've been covering this sector for going on 10 years. And it was interesting because when I first started out and I would talk to the people in the wood processing area, it was kind of more along the lines of, keep those servo things away from us, dang it. I want my AC motors and I want my cams. I'm very happy with my cams, and they work, they don't die, and I know how to work them, and maintenance likes them. It's been fascinating to me to watch the increasing levels of sophistication even in areas like wood processing and mining and steel and so on. taking up the more the electronic technology. And in this case, the example is in wood processing. Now, when the logs go into a mill, first step is debarking. They chunk that stuff off, and then it goes through a rough saw that puts it into planks. The problem is, as probably everybody out here who is an engineer knows, reality sucks, and logs are typically not straight, so they're going to be a little tilted. They may hit the saw skewed, so all of a sudden you're not going to get all of the planks out of a piece of wood that you necessarily would want. So they previously had been able to adjust the blade angle in the saw by about 15 degrees, which, it helps some when things hit skewed. They got about 45 boards per minute, about a 50% yield from what they put in. I assume the rest went into, plywood or particle board or whatever. Not plywood, particle board. But because of easier use, servos and drives that are easier to use, easier to integrate, easier to maintain, they're now starting to move into using servo solutions. That buys them positioning of plus or minus 3 degrees. Yield bumps up. Now you've got 75 boards per minute and a yield approaching 100%. Again, because you've got a much more adaptable system. But the reason it got into the sawmill in the first place is, number one, it's robust enough to stand up to conditions, but also it's user-friendly. It does the job without having, the guy have to go out there with a screwdriver and sit there for a day. So that ease of use theme is one that really keeps coming up. It's not just performance. Materials handling. Now here's another technology, but this is more along the themes of better performance and alternatives. Now remember we were talking earlier about customization and how important it is for customers to be able to have customization, but in order to really execute that, that means manufacturers, your end users, need to have that level of customization as well. Old school conveyors, great, things go on the conveyor, they go on the conveyor the same way, they go to the same place, same time. But that's not always what you want to do. So what they're looking at now is smart conveyors that are able to customize where material gets transported and that are independently routable. And something that's interesting there is some of these intelligent conveyor systems. And they've got autonomous carts. They run on pre-configured tracks, but the route and positioning is not pre-configured. So you look at it as a motor split into two parts. So the coils, your stator basically, that's in the tracks. And then the carts are your rotors. They have the permanent magnets. So you energize the coils, and obviously you've got to have a pretty good controller to run all of this, but you energize the coils, and that pulls along each cart so that you can route it. You get complete custom motion. You can position it where you want to position it. The spacings between carts can change. So there's a lot more choice involved. It's no longer let's be really good at doing the same thing over and over. It's let's get the flexibility to do different things and do them easily. An example of this is Arup Laboratories, University of Utah. This is a big medical diagnostic center. They do 3,000 different combinations of blood tests. And they take tests from hospitals and clinics all over the place. They've got a 2-story refrigerator with up to 2.3 million specimens that obviously they need to be able to trace and track. And they have the intelligent conveyor system because all of this stuff has to happen really accurately, really traceably, and really quickly. So 200 plus meters of track. Each meter has 60 motor coils, and that allows them to process as many as 6,000 samples per hour. With full tracking and traceability, they've got vision, and the ability to follow what's happening. So hold on. Let's see if we can do modern technology here and watch a video. We're not going to watch all of this because it's too long, but it's pretty fun to watch these little guys whizzing around. Oops. Maybe we don't. All right, so this worked when I was practicing. And Joanna, do you have any ideas here?
Yeah, try hitting it again, clicking your mouse right on that play button. Yeah. There it is.
All right. There we go. So all these little guys are independently routed. If you notice, the spacings are different. They can make a pause. And as they describe it, they have them all in binders that allow them to know exactly where they are at all times and then restart anytime there's a fault. And they have the ability to route samples in and out of test chambers for multiple sampling. So I just like watching them whiz all around there. All right, I think we've done enough of that. There we go. So there's that. Other interesting things in life sciences. You've got a lot going on with DNA sequencing and cell imaging and so on. One of the overarching trends that I'm hearing about is the diagnostic equipment for a long time really focused on steppers. But once again, we kind of got the theme that the shift is more towards servo motors now. As long as you've got the high resolution feedback and the auto tuning to minimize settling, you're going to get faster and better throughput. Now, the particular example, actually, let's talk about direct drive motors first. Direct drive motors, frameless motors, kit motors, they have different names, but basically, instead of being the servo motor that gets coupled to a gearbox and then coupled to the load, you've got lots of compliance going on, and of course you've got some size. Instead, you've got a separate rotor, separate stator, get built into the machine, and that's going to give you a much smaller footprint. Definitely you're going to get less compliance because you don't have to deal with the coupling. Downside is they are definitely more difficult to execute. That's where the engineering support comes in from vendors. Anybody wanting to use those would definitely have to be prepared to probably work closely with an integrator or with their vendor. But on the upside, it gives a lot more flexibility for product differentiation, and particularly in the life sciences. They're very complex systems, but they're also, it's kind of hard to differentiate among the various test processes. So that's a way to really kind of get an edge. Now the example here, I think, is a particularly interesting one. And this is for, the genesis was, I believe, at the Cleveland Clinic. And they're working on stem cell activities. And that's something where you can count cells easily, even in low amounts, doing DNA analysis and stuff, doing a technique called polymerase chain reaction, PCR, and that lets you amplify the volume and do a lot of liquid analysis, but it also damages the cells. What these guys want to do is be able to look at these stem cells closely, look at their morphology, watch them grow, see how they act as colonies, but also count them. And that's where the problem comes in, because they tried doing it with people looking through the microscope and counting, and it's just a really hard job. They have to do it through a narrow field microscope. They can't reposition consistently. You get one person counting and another person counts something else. Sometimes you get one person counting today, and when they go to count tomorrow, they don't get the same numbers. It's very hard to see something of interest and go back and find it again. So this group really wanted to find another way to attack this so they could continue their research. So they decided to develop their own system. And that would be based on digital imaging. So instead of doing the single count kind of thing, you get a CCD camera and you do a set of images, you stitch them together, you digitize it, and then you're able to review it and compare and have a history and so on. So in theory, it sounds great, but you've got to have the right equipment to carry it out, and that gets us back to our same thing. You want stable point-to-point motion. They need to be able to move the field of view of the imager and do it repeatably, reliably, very accurately, and rapidly, so that you don't have a lot of settling time. So, once again, we're talking about making the technology that's giving high performance and ease of use. So what got pulled together on this, that should be photocredit Parker, Hanifin. They did an automated imager with a wide field microscope, CCD imager, and the XY stage is based on direct drive motors. So instead of having to do the gearbox and the couplers and all of that, they did direct drive. And part of that was because they wanted a really low profile on the sample positioning. Any of these, the wider the field of view, usually the more narrow the depth of focus. So you don't want to have the sample too far away from the microscope. You want to be able to really get in there. These devices wound up with 0.1 micron positioning repeatability, and initially it was developed as an experimental system, but my understanding is Cleveland Clinic, along with several other organizations, are now working to commercialize this as a system for sale, so that other organizations who are doing this kind of research would be in a position to buy it. So, it really could forward that technology. Another factor is safety. And again, I was talking with someone just the other day who said, it's been out there for a while, but it really just seems like it's only now being, taken up, to a level where people are really taking advantage of it. There's safety and there's safe torque off, but you can go a whole lot further with some of the new safety drives and safety PLCs. And I'm going to give a couple of examples of that here in a minute. But you wind up with the ability to speed productivity, optimize operations. You can even simplify maintenance. Because it's important with safety. Obviously, OSHA, you don't want people to get hurt. That's first and foremost, is the most important. But you also can use these technologies to protect equipment and to operate the equipment more not intelligently, but more effectively, in a way that lets you, again, spend more time making things and less time taking care of things. Printing. If you're cleaning rollers, you clean and jog, and that can be very time consuming. But with some of these safety components, you can use safe direction, you can use safe speed, and suddenly instead of doing clean and jog, you can be doing that continuously. And machine builders can even design that in, so you would have an automatic cleaning routine. And again, less time spent on the maintenance type of thing means more time in operation. And I can give you a direct example of that. Food and beverage. So this is a food and beverage manufacturer. Again, they did a clean and jog. That was clean, get out of the enclosure, jog the machine, go back in the enclosure, turn it off, go back in the enclosure, clean, go back, take torque off. And it took 6 hours a day to do that. They put in an advanced safety system that let them use safe speed and safe direction, and also a safe position protocol. So now they could do limited safe operations even when the enclosure was breached. That sped up the cleaning process to less than 2 hours a day. So it goes from 6 to less than 2. 4 hours, half shift of production. That's kind of an example of where safety really goes. It's not just light curtains and let's keep people's fingers from getting munched. It's let's make the technology work. And this kind of goes to the secondary theme that I heard when I was talking with people, which was not just new technology giving us entree into non-traditional areas, but traditional manufacturing areas doing a better job at what they do by adapting some of the new technologies that are out there. Second example of this, electronic fuel injectors. In this case, the operator had to break a light curtain to adjust the part and the machine pulled away. Now they did have fairly sophisticated safety because they were able to use safe limited speed to pull the machine away rather than have a safe torque off. But the thing is, if you look and you analyze the application, the risk was really if the motion was moving toward the operator. So what they were able to invoke was safe direction. And that meant that as long as the machine was pulling away from the operator, it could go at top speed. It didn't have to go at safe limited speed. And that resulted in a 10% reduction in cycle time. Now, this part is really kind of getting more into what I've been hearing a lot about what's going on in your traditional areas, again, like pharmaceutical, consumer packaged goods especially, also food and beverage. And it's got to do with using some of the technologies for network stability and so on. Initially, what I was hearing a lot from, especially analysts, was, the OEMs are the ones who are really excited about, being able to do all these analytics and being able to have their machinery, online and all of that. The end users don't really care all that much. In the last 6 months, that really seems to be changing because increasingly when I'm talking to people, I'm hearing that, your big food manufacturers, your big, again, consumer packaged goods, they want any edge they can get. If you're making diapers and you figure out a way to make one more diaper an hour, that's an edge, or one more diaper a minute, that's an edge. And that's something that we can add up. Remember back to the electronic pick and place. So these guys are increasingly waking up to the the notion that there's a technology out there that is going to be able to give them an edge. And one of the analysts I spoke with a couple of a month or two back, who was doing some big data analytics, said that in the next year he's expecting an absolute sea change in the technology uptake in the end user community, that it's really going to get to be a big deal. So what is the saying? Lead follower, get out of the way. If you're at the back, the view's the same. So let's run through me waving the flag here, which is, there was the old way of doing it. Do it by hand, yawn. We don't do that anymore, or we don't have to anyway, because you've got technology on your smart components that can gather that information, and they can deliver it up to the operator so that they can maximize, minimize idle time, changeover time. They can adjust in-feed speed. They can adjust scheduling. You can do analytics comparing how all of your machines are operating. And part of the reason that we can do a lot of this is because we've got equipment that is completely connected, or I should correct myself. We have equipment that can be connected, and very often the equipment that's out there could be handled in this way if people want to do it. So you've got the various kinds of sensors, you know what's going on with the equipment, and then you've got the ability, because of the network level connection of components, to send that information wherever you want to do it. Now that was one of the things that really came up again from the usability standpoint, talking to folks for this project, which was end users and OEMs like the fact that you've got network-ready components that you can run your machine networks, you plug in, you can get to the whole machine, you can find out what's going on with the equipment, and so on. So the question is, how far do you take it? You can get that data, and if you're running it via industrial Ethernet, you can pull it together, you can send it off to people on the top floor for analytics, you can communicate to other machines for better operations. You can also get it to your maintenance department, which gives you predictive maintenance. And this goes back again to that ease of use, to making OEE better, because you're going to help reduce your downtime, because the sensors and the information that you're getting from your components is helping you figure out what's happening in advance. I mean, it used to be something broke, you fixed it, and then it turned into, fix it on a schedule, whether it's broken or not. But now with the technology that's out there, you can do predictive maintenance, which is going to tell you in advance whether you've got a problem. You can be monitoring how much wear is on the equipment, but you can also look for damage frequencies. If there's a change in that, then you know there's something going on, and these systems can notify maintenance, so that maintenance either can take care of it or maybe change how they're operating the machine. One of the things I've heard from maintenance folks as well is they get a day of downtime, or they get once a month, once a quarter kind of thing, and they usually have to figure out how it is they're going to spend that time, because there's just not time to do everything. And this kind of thing can really help getting that visibility. Now, there is a caution here that goes back to the adaptive drives I was waving my arms about earlier in the discussion, because the adaptive drives are designed to see issues showing up with the machine and adjust automatically to help optimize the performance of the machine. The danger there, it's just to keep in mind, is that that can mask one of these problems. So it is really important to make sure that in these kind of systems, it is set up, as I was talking about earlier, to notify maintenance and operations, hey, I made a change. I saw something different. I'm going to keep everything running okay for now, but you need to keep an eye on it. So just kind of something to keep in mind. But again, the benefit of the connectivity is that it can minimize downtime. It makes it easier to manage the equipment, lets people reduce inventory levels because you got a more flexible system, greater degree of customization, lower costs. The equipment becomes sort of an easier to manage set, if it makes sense. And let's take a look at one example of how that might manifest in the real world. So you've got a beverage packaging line, and all of your equipment is connected. So your machine jams, and you've got intelligent line control because the status of what's going on with all of your machines is all being overlooked by your supervisory system. So now one of the upstream systems can slow down, downstream system slows down, you've got more time to clear the jam, and then the line goes back to full speed. So overall, instead of having to shut everything down, you're able to just have sort of a slow type thing. And this kind of moves into where we're starting to talk about manufacturing execution systems and SCADA systems and geoscada, where you're not just communicating across the factory floor, you're communicating at multiple facilities. So if this kind of slowdown affects the facility elsewhere, you're able to transmit that information. And then one last thing that is starting to really attract a lot of attention, again, a lot more buzz in the end user community, I'm told, is power management. Servos, about 25% of the servo system operating costs is represented by energy. And also energy costs can be controlled by when you're using that energy. You get dinged for your peak energy draw. And if there are ways that you can adjust your demand so that maybe you're not doing high energy activities at the during the peak daylight hours, or you're spreading them out instead of doing them all at once. You're doing something so that you don't wind up with a massive energy spike. Now, that's given or created a lot of interest in energy monitoring, and this is where we get into one of the trends I was talking about up above, which is software that comes pre-configured and so on. Now, there are ways to do it yourself. It's expensive. It's not easy. It's kind of like trying to do an ERP system yourself or something. But increasingly, there are purpose-built energy monitoring systems, not just in hardware, but in software. So you've got systems that are pretty straightforward to put together, and you can get really granular data out there because what you need is to understand what the system is doing. You can't make decisions until you know about that. And there are nuances to how to execute this and so on, but I did want to show you guys at least an idea of some of the options. There was an example that I had hoped to include on the application and that I was not able to, but one other trend that I want to hit in this software side of things is there's an increasing trend toward pre-written software, I guess, for a better way of saying it. There, in the sort of larger developer community, there's something known as API, Application Programming Interface, and the idea is that, I don't know if you're a bank, you do little subroutines for e-commerce. So if you're a developer, you don't have to write that financial transaction part, you just use the part that the bank put together. You know, similarly, like a weather.com sort of thing, or a weather company. They would do an API that would just be on weather that other people could use. And that's an increasing trend in the vendor community to develop those kinds of subroutines so that when you've got OEMs and integrators trying to program systems, they don't have to build everything from scratch. They don't have to write the file handling or maybe access control or some of those types of details. That stuff is out there that they can access so that they can worry about actually building the machine and installing those servo motors with the drives that have auto-tuning that makes that part easy. So they can really worry about kind of the key things that differentiate them as machine builders. So there's that, and I believe that brings us to the end. So yeah, I mean, to me, the dominant theme based on talking to people is really in the vendor community. The big focus has been on end of use or ease of use, and that's creating a lot in new applications. The other thing is performance improvements that are really starting to further some existing applications. Key technologies, again, auto-tuning drives, intelligent conveyors, frameless motors, I've been hearing a fair amount about. Networkability, definitely, and the pre-configured software. And with that, I think I just snaked in under the hour. So Joanna, I'm going to turn that back over to you.
Great. Thank you, Kristen, for the informative webinar. And again, I'd like to thank our sponsors of this webinar, which is Kollmorgen, Nexcom, and Nexen, and of course our participants like you. If you did have a question for Kristen that you had during this webinar, please go ahead and submit them in your questions panel, and we will answer those via email after this webinar has concluded. And as a reminder, you will get a link to this recording within the next 24 hours. If you're looking for upcoming webinars with motion control, be sure to visit our website, which is www.motioncontrolonline.org. And with that, thank you for tuning in. Have a great rest of your day.